Hi guys, I'm Napu, and today we're going to be doing a math problem. Okay, so you are on an airplane and your flight is 7 hours long. Currently, 5 hours have passed. But you want to figure out the distance the airplane has traveled so far. So you look if there's one of those in-flight maps that shows you your location. But all there is a screen that gives you the time in knots, which is nautical miles per hour. So if the equation of the airplane's velocity is this equation right here that we have, how far has the airplane gone? And so the way we're going to solve this is we have to recognize that this is a velocity equation because it gives the velocity of the airplane. And velocity, as we know, is the first derivative, and this is going to be very useful to us. So if we sketch out like the graph of it, then we can like kind of figure out that we're going to need to find the area under the curve, which is the integral. The reason why is because on a velocity graph, the area under the curve of the integral is equal to the distance. So the idea is we're thinking that this is a velocity function, right? And so since velocity is the first derivative, there has to be an original equation from which velocity is the derivative of, since it's the first derivative. So we're going to try to find that equation, which is also known as the antiderivative. So usually we're given the equation and we have to translate it into getting the derivative or differentiating it. But in this problem, we have the derivative and we need to get to the equation, the original equation. So that's finding the antiderivative. And so we're going to try and find it. But first, I think we should practice because integration can be kind of hard. And so we should start off with a more basic example. It's like y equals x squared. So, for example, here's the graph of y equals x squared, or like I just kind of sketched it. And we got to figure out how to find the area under it. So if we zoom in, it's not exactly like an easy thing to find the area of. There's no magic formula like a square or a circle or rectangle, so we're gonna have to try guessing. Let's just try it, just give it a shot. So one way is to approximate using rectangles, right? Like this. It's not very accurate, but if the thinner you make the rectangles, the more accurate you get. And you'll notice as the thickness of these rectangles gets closer and closer to zero, the more and more accurate your answer will be. And this is a very beautiful thing that is kind of like the center of calculus. Like, I mean, you see it in limits and in derivatives too, right? As you get closer and closer to zero, not at zero, but as you get closer and closer to zero, you get closer and closer to the answer or to what it approaches to. And that's pretty important. So with this in mind, we can kind of find the area. So each rectangle is has a formula for the area of y times the thickness, dx. So y is the output, and it measures the height. So we can say that the integral is the sum of the area of all these rectangles, or in calculus, in the integration notation, we could put the little s symbol that stands for integral, and we can put y in dx. And so we bring this back to y equals x squared. What's the integral of x squared dx? So we need to find the antiderivative. So the way we're going to do this is the antiderivative is like it's the opposite of derivative, right? So the derivative of what will be this? So the derivative of what will be x squared? So in order to visualize this, we kind of have to go backwards, right? So using the power rule, you know that when you have the derivative of something, it's usually one power less, right? So like you have x cubed, the 3 will hop down to the front, you'll get 3x squared, right? The 3 goes down to 2. And so this is important because we can tell that since we have x squared, that the answer, the antiderivative, will contain x cubed. But if we find the derivative of x cubed, we know that it's 3x squared, right? It's not x squared. So to neutralize this 3, we need to have its reciprocal as a coefficient. So 1/3, we're multiplying that by x cubed. So 1/3 times 3 equals 1. And we had to add c to it for the antiderivative, but I'm just gonna kind of like ignore that for this video because I need to explain that, and that's gonna put me over time. So skip that for now. Anyways, now let's tackle the big problem. So we have the derivative, and then we in brackets we have our equation times dx. So you might be thinking, what's this? How are we gonna solve this? This is crazy. So anyways, let's break it down. So at its root, this thing is a cosine equation, and so you can just kind of like highlight it in red. So the quick question, what's the antiderivative of cosine? So we know the derivative of sine is cosine, right? So if the derivative of sine is cosine, antiderivative is the opposite of the derivative, then that means that cosine's antiderivative must be sine, right? It only makes sense? Yeah, so that's right. Antiderivative of cosine is sine. And so that's going to be very useful later on. Keep that in mind. Also, we have a 250 here in both terms, and because of that, that means we can factor it out, kind of like the reverse distributive property. I don't know. So we can factor it out, right? But we can also factor it out of the integral entirely, kind of like how you can in derivatives, um, you don't do it to the constant, right? You only do it to the terms with x in it when you derive. Similar. So that's pretty important. And furthermore, if there are two plus terms, which we have two terms, you can find the antiderivatives of the terms separately, which is pretty important. So we can find the antiderivative of the cosine and the antiderivative of 1. So let's go ahead and do that now. Let's find the antiderivative of 1, since it seems simple, right? So what's the antiderivative of 1? Well, we can also ask the derivative of what is 1? It's the same thing. And we know the derivative of x is 1, right? Because any term that has x in it is just the coefficient. Because the x to the 1 power, the 1 goes down to 0, right? And the 0, x, anything to the 0th power is 1. So the derivative of x is 1. We can replace that with x. So that's pretty helpful, right? And now we have just the cosine, right? We have the cosine thing that we have to solve. And given it's pretty complicated, but we have a technique called u substitution, which is pretty complicated, but it'll do the job for us. So basically we replace the angle with a u, and then we find du, and we use that to, we divide out from both sides to isolate the dx, so we can substitute whatever we have for dx. And so we figured out that dx is equal to 7 du over 2 pi. And we substitute that into our equation like this. And we have a constant here, right? So the constant means, kind of like the 250, since it's being multiplied to the equation, we can kind of just factor it out of the integral. So we do just that. So now we just have an integral of cosine u, or I mean, antiderivative of cosine u times d. And if we paid attention to earlier, the antiderivative of cosine is sine. And this is pretty important, right? Because I said it was going to help us later on, and it's helping us right here. So we can kind of just take out the antiderivative, and now we just have sine u. And we take out the du too. And now we just substitute the u in for whatever the angle was before, 2/7 pi x. And we can kind of just start canceling things out, use a distributive property to distribute the 2x. And we kind of get our final equation right here. 250x minus 875 over pi sine of 2 pi over 7x. This is kind of a complex answer, right? And so I think we're done, right? Right? We're done? We're done? No, we're not done. This is a long problem, sorry. But anyways, the problem is asking for distance, so we have to find the distance now. So how far has the airplane gone? That's something we need to think about. Well, we have an equation here telling us exactly how, so it's not hard. We just have to substitute 5 into the expression since it's 5 hours, and eventually we'll come out with our answer, which is 1,521.538 nautical miles, since it's knots. And so we have figured out that after 5 hours, you have traveled 1,521.538 nautical miles by airplane. So that's our problem, and I hope you learned something. Thank you for watching. I'm sorry if this is any confusing, but thank you so much.